Hi everyone, my name is Maria and I'm a bridge designer. I'm working for the Latvian company Sia Sigma. Long time ago, I got my qualification in Russia, St. Petersburg, and worked there as a bridge designer in different roles for 14 years. Back then, I was sent to Uzbekistan to teach young engineers how to design pre-stressed bridges. But to be honest, I had no clue what it was. There was no course or even a book about it in my native language. My manager just told me that I would definitely figure it out. No support and no one to ask. Hope those young engineers can't hear me now. At that moment, I found a lot of information about pre-stressing in MIDAS Civil webinars and sharing materials. And finally, I did figure it out. Now I want to show you all how to design pre-stressed curved bridges according to Eurocode, in case you are sent to the middle of nowhere and get stuck with the pre-stressed curved bridges. What the webinar is about. We'll consider design of a superstructure with a post-tensioning system. We'll consider the erection technology, as the calculation model will be directly linked to the way it's constructed. At the same time, we will consider the general characteristics of similar spans, span length, girder heights, and high-strength reinforcement ratio. Then I will show how I created a structural model in Civil NX. It will be a simple beam, however it's curved. Let's see what the new generation of MIDAS Civil will offer us to work with curvature. The stages of making the model will include creating the cross-section and creating time-dependent material properties. Next, I will show the loads. These are permanent loads, pre-stressing loads, and again how to cope with the curvature in terms of pre-stressing. And we will have a look at temporary loads. We will need groups to account for the construction stages. I will show groups of elements, boundary conditions, and loads. We will analyze the results, consider what is included in the combination of the serviceability and ultimate limit states, and discuss how they differ. Talk about the secondary and primary moments due to pre-stressing load, so brush up our knowledge on structural mechanics. We will carry out checks with the help of the module for PSC checks in Civil NX or MIDAS Civil. Then we will analyze the displacements to assign deck movements for the joints and bearings, taking into account shrinkage and creep. Finally, we will go deeper and try to play with the positioning of tendons to adjust them for better use. Let's get started. Part 1. Introduction of post-tensioning pre-stressed bridges. The slide shows the design of our deck span, the modeling of which will be discussed. 3 spans, 15, 24, and 18 meters. 1 rib, 1,200 millimeters high in cross-section, diaphragms on each support. The span is supported on spherical bearings. Now let's consider technological sequence of construction works, because it will affect the final internal forces in the structure. The sequence includes several stages. At the beginning, we install scaffolding, assembly of wooden and metal formwork to hold the structure. Then, construction of conventional reinforcement framework, and layout and installation of ducts and high-strength reinforcement cables. Installation of technological shelters. Later, cast of the first span or first segment. When the concrete has gained strength of 80%, tensioning of tendons is carried out. Then the anchor tenders and install couplers to stress the cable in the next part of the deck, which has not been cast yet. After that, cast the second span. After the concrete has gained 80% of stress, tensioning occurs. After this stage, the scaffolding might be dismantled in the first constructed span. That is how we can save money on rating the scaffolding and move it to the third span, the last one. Then we do the same with the third segment of the deck, repeat cast and stressing. So all the deck is cast in tension. Then we do grouting, injection of ducts. After all, dismounting of technological shelter and deleting scaffolding. Here is the layout diagram for high-strength reinforcement, cables. The cables is laid out according to the diagram of permanent loads. In the middle of span, the cables are located at the lowest part of cross-section, creating a moment opposite to external load. Above the support, the cables generally are in the upper part of the cross-section, counteracting the hogging bending moment. We will discuss in detail how to position the cables or adjust the profile in the most favorable way when we discuss the result of the calculation. If we discuss why we use pre-stressing here, then for spans of more than 15 meters, it's not enough to use the conventional reinforcement. I want the level arm in the cross-section to increase and absorb the bending moment. Due to the increase, the weight is going up and again increases the moment. So it's impossible to achieve equilibrium, therefore pre-stressing is required. The pre-stressing is designed to remove the tensile stresses in concrete, since this material doesn't work well in tension, and to reduce the deflection of the structure. Note that in a simply reinforced beam without pre-stressing, the concrete in the tensile zone is just to hold the steel in place. And this material in this zone adds more weight, but it does not use the strength of this material in any way. As can be seen from the design diagram on the right, a uniformly distributed load acts on a simple rectangular cross-section beam. The section is subjected to compressive stresses at its top and tensile stresses at its bottom, which are equal. If we add a central pre-stress, the tensile stresses will decrease by value N divided by A, whereas N is the pre-stress force and A is the section area. And if we apply a pre-stress lower down the section, in addition to the uniform compression, there will be a moment from the eccentricity of the compression force, and the stresses diagram from the pre-stress will take a triangular form. Thus we can increase the load or we can increase the span. Today we are considering a system with a post-tensioning. Cables will sustain after the concrete is cast and strengthened. Considering the characteristic of this type of superstructure, the following can be noted. The designer's task is to find the optimum height and width of the rib. As shown on the previous slide, the stresses counteracting external loads depend on the position of the pre-stressing force at the height of the section. In other words, on the height of the beam. While reducing the height, the width will increase to provide sufficient ultimate strength. As a rule, the bending moment at the supports is the governing criterion. As the height decreases, the level arm in your section will decrease as well. Hence, the stresses on the fibers will decrease too. Although the pre-stressing force itself will remain the same, the same amount of pre-stressing reinforcement in the section. Plus, the weight itself will be greater with the wider beam, and the moment from it will increase. As a result, the external load, self-weight, will increase, and the restraining moment caused by pre-stressing will not. Therefore, if possible, one should try to make the beam higher and thinner. The average ratio of span length to beam height can be considered as 1:20. Similar spans of constant height are used up to 45 meters, with an average consumption of high-strength reinforcement of 50 kilograms per 1 meter cubic. The beam width is constant and is determined by the following parameters. First of all, space for placing anchors. Then, compressive stresses from bending moments. Serviceability limit states considered. Also, ultimate moment in the over-supported section. This is ultimate limit state is considered. And ultimate shear force and torque. In the picture from the book, noted below, you can observe how the height of the beam varies with the width of a 35 meter span. The effective ratio of the outermost spans to the center spans is 0.9, which is a consequence of the secondary moment, which we will discuss later. The effective scheme is not a 3-span scheme, but a 4-span scheme. The reason is the same. We are going to part 2, model description and definition using plug-in. First of all, we need to create sections of the main beam. I create the section in AutoCAD with the compliance of Europort Chapter 7, Clause 2.3. Thus, I will have 3 sections in AutoCAD. For purpose to account for these varieties in sections, I use effective width scale factor. Very convenient function, I definitely recommend. On the slide, I put the screen of my Excel where I prepared the characteristics of all cross-section and calculated the scale factors. Next, I created the biggest section. This is section 3. In section property calculator and export it to MIDAS. Fill the section's dimensions there. I want to mention that there are 2 positions, Z1 and Z3. Those points will deflect in results. We will be able to check stresses at these points in terms of decompression, the most severe requirement at serviceability limit states. Next, we need to create the beam axis. To do so, I will use in MIDAS Civil plugin alignment generator. I'll try to show you. Here is the model. To create the beam axis, as you see, it's curved. To create the beam axis, you will need to go to the tab apps, find the plug-in, be assured that it is connected. Then click on plug-in and find the alignment generator in Marketplace and click Run. There are 2 tabs. On the tab Alignments, enter the parameter of the axis. It should be longer than your design or equal. In current model, the axis was consist of 2 line types. It was straight and arc, so I needed 2. On the tab Segments, you can set the length of segments and the number of times of these segments, like that. After that, you can click Create, and you will get elements aligned with the structure axis. I will do so because it is already created. So let's return to the presentation. So remember, we can't put the same section along the whole axis due to non-uniform stress distribution. See the paragraph 7, clause 2.3. Geometric data. It is called geometric data. That is why I created 3 sections. Now it's time to put the scale factor into the model and using effective with the scale factor function. Go back to the model. Here you can see effective with scale factor. It is on the work tree. I ask the program show me the table you will see those values that I calculated on the previous slide in my spreadsheet according to the 3 types of sections. And also you will see that they all are in one boundary group. I will show you what this boundary group is. As you see, it is the last in the boundary group, section 1 effective width. If I ask to show what it is, the program will highlight those sections, because the largest sections with 100% is positioned in the middle span, and other sections, they are put in those boundary group, and now it's highlighted like that. Boundary group is needed to be able to operate the width of section in relation with the stages of construction. Here is the final bearing conditions in the model. First of all, I created links to simulate the height of the section at support points. I choose rigid link for this purpose. It's represented as pin links with 3 nodes. Then I used elastic links, type general, to create the supports. In each elastic link, type general, there are 6 degrees of freedom for movements and rotations, to which you can assign stiffness. For the supports used in this model, I choose 3 rotation, but they will have some stiffness in the transverse directions and in the vertical directions. Naturally, a very large stiffness in vertical direction. The small indexes indicate the use of local axis. In this case, the axis of the link itself, the x-axis, will connect 2 nodes. By x, the vertical stiffness. Here, they are blue colored. Also, to account for the curvature, it's compulsory to rotate the links aligned with direction of bearings. I'll show you in MIDAS model, here, yeah. I'll show you how they looks like. So this is elastic links. As you see, I can show it in plan view. They are rotated. They are aligned with the scheme of bearings that we will discuss later. Also, I show you the rigid link with 3 nodes. Display at support sections, as you can see. Let's turn to the presentation. In terms of bearings, on the scheme of bearings, you can see the deck is fixed longitudinally on a single pier here. This is the scheme where bearings aimed at fixed point of the deck. They are not aligned with the axis. So all fixed bearings rotated in direction to that point. And the final step is to create the supports below blue links, which are fixed in all directions. When modeling with MIDAS Civil pre-stress structure, concrete structure, it's necessary to set the stages because the strains and stress in pre-stress concrete bridges change continuously over a long period of time. This is due to the time-dependent properties of concrete and steel, such as creep and shrinkage, steel relaxation of tendons, pre-stress losses, and also due to variations in loads or support positions, namely different phases of bridge construction and differential settlements of supports. What we will get using function construction stages. It gives an analysis of the stress state of the intermediate stages of the structure. For example, span without asphalt at the stage where we just have stressed the concrete. Without asphalt, it's possible to exceed permissible value of stresses. Or, in the process of erection, the deck is supported by temporary supports. Creep and shrinkage also change the stress state of the structure over the time. Staging is necessary to accumulate and preserve the history of the stress state. Stages are defined by duration. The structure can be permanent or temporary. In a stage, it's possible to activate and deactivate elements, boundary conditions, and loads. So, step by step, we reach the final state of the structure. What about stages in the model? Our staging consists of 10 stages. First, build the scaffolding and cast the concrete. The concrete gains strength. Second stage, tension the cables, each tendon in turn. Losses are released, losses due to friction, due to slippage of the cable in the anchor, and also losses due to elastic compression of the concrete. Then we repeat two previous stages with second and third segments. These are stages from 3 to 6. Stage 6 also do grouting, injection of ducts. Stage 7, remove scaffolding, self-weight continues to operate. Stage 8, add load from asphalt and barriers. Stage 9, 1 year, just to follow changes in strains and stresses from creep and shrinkage. And stage 100 years, it's the operation phase of the structure to check whether it is okay due to time-dependent properties of materials. To be able to manage the stages, it's needed to create structure groups, boundary groups, load groups, and tendon groups. Let's look in the model what it is included. Here is the model at its base stage. I will quick show how look each stage. This is when we cast concrete. As you can see in work 3, there is no load, just self-weight. Also, boundary conditions. It has the restricted boundary conditions on the second pier, and it has a lot of spring supports. They are modeled to create scaffolding. By the way, how to create them? As the nodes of the beam does not have constant pitch, I use surface spring. Go to the boundary, and here you can find surface spring. It will calculate the point spring in each node with its thickness in relation to the length of the particular element. The print screen with the values which I use are given on the slide of presentation. Okay, let's go. So we have some boundary conditions and some loads, and of course some structures. Then we go further. The pre-stress occurs on this stage 3. We do casting the second segment. 4, we stress more cables. 5 and 6 the same. 6 is the last, and when we do grouting, then we apply asphalt. As you can see on the, here we remove scaffolding. So here you will not find any point springs. because there's only the final supports. Then we have 1 year and 10 years. Let's consider one stage in details. For example, stage 1, show. Here we have 2 tabs, element, boundary, and group, and the list below shows us what groups do we have to account for. Here I have first segment, main beam, and peer 2. Peer 2, I need to put their nodes as well, because if I do not put in the tab element nodes, then any boundary conditions that you add to this stage will not appear. So you need add peer as an element and boundary conditions as well as peer if it has boundary conditions. And load, we put self-weight here. I will show you what it is. Group of elements with peer 2, yeah. You can see that they are here, and it has 5 nodes. So with this group, we are able to add boundary conditions if they are including boundary group as well. Now let's look in details at stage 100 years. It doesn't have any element groups and or boundary because it's already, the structure exists, so you don't need to add anything. And the load, there is no load. It just has a duration to account for creep and shrinkage. Let's find where effective with scale factor boundary group appears. So here we have at the stage 100 years, of course, it exists. You can see it here. But from what stage it occurs? At stage self-weight, when we remove scaffolding, it exists. So we account for it at stage self-weight. And when we just construct our structure, there is no boundary group effective with scale factor. So we discussed how it's possible to operate with elements, boundary conditions, and loads over time. Let's go to the next slide. To allow the software to take into account the changing properties over time, according to the stages of the structure existence, I need to create the corresponding concrete properties, and then they need to be linked into one material. It's very easy to do, but also you can do it by the plug-in. Here you don't need to put any figures, almost nothing, just choose your standard. Here we choose European, so mean Eurocode. Here we will write the local humidity and below the notional size of member. I think that the surface that is covered by waterproofing material and therefore doesn't touch the atmosphere should not be considered in the perimeter that is accounted for this formula. So I excluded from the perimeter. It is shown below here what I put in the formula. Go further. It's time to consider the tendon property. The tendon used in the model consists of 19 strands with diameter of each 15.7 millimeters, One strand has 7 wires. When we create the tendon property, we need to calculate the total tendon area. It is done with those data. Then we have to choose the duct diameter. This all you can take from the particular product supplier booklet. Ultimate strength and yield strength also goes there, but you can also take it from Eurocode, as I remember application K. Curvature friction factor is given here below. This is the screen from the Eurocode, but you also can take it, and you need to take it from the particular product supplier booklet who will do stressing the deck. And unintentional angular displacement is given here. You can find the paragraph and clause where it is written. Natural slip, usually it's from 2 to 6 millimeters, and here we use type bonded. Characteristic strength and yield strength, this is the yield strength, is shown here, and how they compare or differ to each other. So that's it. This tendon property will affect on your tendon losses, so it's quite important to feel it right. Go further. Next, we need to create tendon profiles. For that purposes, I will use Excel spreadsheet with coordinates, and I will copy there the command TND profile from MCT command shell, and that is how I will get the final command with tendons coordinates. I will look at in my spreadsheet. Let's have a look at it. Yeah, here it is. So I have coordinates for all tendons here. Then I copy the command from the MCT shell, and finally I make this sheet with all the names of tendons, with all the coordinates that are linked between each other, and then I need just to copy everything like that and put it into the MIDAS MCT command shell. MIDAS apps, go to tab apps, find the MCT command shell and do like that. Okay, I didn't copy. After, click run, and the tendons will be created. Those profiles will refer to the element, and their curvature type will be spline. Here you can observe the graph of tendons according to the particular construction stage. I always create graphs in Excel to assure that my coordinates match with peer axis, ends of segments, and between each other. Here is depicted the red cable. We stress it at the second stage. Only 2 cables. Then blue tendons are stressed at 4th stage. There are 3 cables. Yeah, the 6th stage is given here, and finally, I put all together just to be sure that they are matched between each other. I always create graphs in Excel to assure that my coordinates match. Yes. Here is the sequence, what we need to do to create the right tendon profile for curved bridge. Let's imagine that we've handled with creating profile coordinates in Excel. Add the command in Excel and then copy to MIDAS Civil through MCT command shell. So we get the profile with reference access to the element. Then we need to change it to straight. Why we do this? The MIDAS will not calculate some of the pre-stress losses which account for the curvature if the tendency is referred to the element or to the main girder in our case. So we need to go to the plug-in again and launch tendon profile. It will convert profile into straight. Coordinates will be in relation to the model coordinate system. It is quite straightforward, and it makes your life easier if you're an engineer, of course. After you have changed the type of axis reference, don't forget to check the point of jacking. The beginning of the straight tendon aligns with the model coordinates, so choose the right point from where to stress. Next, let's create the pre-stress load. For that purpose, we need to choose the pre-stressing force, and it's not as easy as it could be, like many things in your code. I'll show you what are the limits for this force, and then we will quickly see how it's organized in the model. So maximum jacking force, according to Eurocode, is Pmax. But you can increase it. You can use a larger force. It's called overstressing. Permitted overstressing here. And the force of permitted overstress. But you have to be sure that your stresses after immediate losses will not exceed the value of maximum jacking stress. So it can be an iterative process. Usually, immediate losses are about from 7 to 15%. We will check it later. Let's go to the model again. And go to the tab load, find the pre-stress. We've already created tendon profiles. Now we need to stress the structure. So I click on tendon pre-stress. Here we will see that it is the cable is already pre-stressed. Each cable has its own load group because I want the program to account for elastic shortening pre-stress losses. You can see the first jacking begin, you choose end or both, and the force with which we will stress the structure. And also here you can see the grouting after. That means that grouting occurs after a number of stages from the current one. That's it. Let's go to the presentation again. Before asking MIDAS perform analysis, we can go to tab analysis and click on construction stages. Tab analysis, click on construction stages. And adjust there some effects. Time-dependent effect. It's responsible for pre-stress losses. Also, we can exclude part from dead load from construction stage output to assign it in a specific safety a specific safety factor in our load combination. In that model, among all variable loads, I considered only live load, group of loads GR1A. Look at the Eurocode actions on bridges table 4.2 and 4.4a. To define live load, namely LM1, we need to do the following steps. Define traffic lanes, define vehicles, and define moving load case. Tandem system and UDL system with magnitude 9 kilonewton per meter square and magnitude of 2.5 kilonewton per meter square on the remaining area are depicted here. The same load arrangement you can observe in this picture from MIDAS Civil NX. We finally got the modeling part. Now it's part 3, result analysis.
So we asked MIDAS to analyze the structure. What's next? Let's consider pre-stress losses because they will significantly influence on the internal forces of the structure. They are divided into two types, immediate losses and time-dependent losses. Eurocode says, at a given time t and distance x from the active end of the tendon, the mean pre-stress should be taken equal to the maximum stress imposed at the active end, where you do jacking, minus the immediate losses and the time-dependent losses. See the equation on the top right of the slide. Immediate losses include friction, anchorage slipping, and elastic shortening. If we talk them in particular, friction, the cable wraps on the sides of the duct and loses tension. Next, anchorage seating. Due to it, the shortening of tendons occur. Usually it's in the range of 2 up to 6 millimeters. That causes the loss of pre-stress force. This loss due to slippage are largest at the tensioning point and are compensated further by friction. We will see the pattern of it in the graph of tendon losses in MIDAS results. Next, elastic shortening. We stress the first tendon, there is no elastic shortening, no losses. Then we stress the second tendon, no elastic shortening in the second tendon, but losses occur in the previous first tendon due to the concrete shortening by the force of the second tendon, and etc. with the following tendons. Physically, these losses are easily to imagine if you wrap a cable around your hand. One end hangs freely, there is no tension in it, and the other end is stretched by your hand. There is tension in it. This difference is the tension lost by friction. If you move the tensioned end to the side of your hand, like that, in other words, you imitate the anchorage slipping by few millimeters, the tension at the hand will decrease here. But you can feel closer to the middle of your hand that there the pressure force has not changed much. And this difference is again caused by friction. And of course, at the beginning of the hand, there is no friction loss due to existing anchorage slippage effect. That is why we choose the smaller value of losses between two. So we choose the smallest value of the two losses in the calculation and do not sum them all up. Now let's see in MIDAS what these losses are. We are in the program to look at tendon losses. Go to tab Result, Result Tables, Tendons, Tendon Loss. As you remember, a tendon in group tend1 are stressed at the second stage. So MIDAS shows us there is no stress in it at the first stage. I changed the stage and got stresses after the stage 2. There are immediate losses, friction and anchorage seating. To check whether you choose the right jacking force, I showed MatCat previously, you need to know stress in the tendon after immediate losses. Here it is. But I will add to immediate losses elastic deformation losses because they arise directly during the tensioning. As can be seen, losses due to creep and shrinkage are insignificant at this stage because there was no time for them to realize. Let's turn to the next tendon, to the longer one. It is in the group tend2, the blue, because the graph of it will be more representative. And you can see on the graph that losses from the active anchor decrease to passive one because of friction. In addition, it can be seen that there is a short section on the active anchor, beginning of the graph, where losses drop dramatically due to anchorage seating. To avoid mistakes, here you can easily check whether you choose the right position of tendon to jack in your model. Also, there is a queued function. You can ask to animate tendon loss over the life of the deck. We have now verified that MIDAS calculates tendon losses, and we can even distinguish them on the graph among different tendon losses. And what about checking results according to Eurocode? Let's return to the presentation. On the next slide, here are formulas for how stresses are determined at various stages of structural performance. And the summary from Eurocode on permissible stresses for the deck depending on the exposure classes. I tried to prepare a small spreadsheet about these limitations in relation to the exposure classes, the grade of concrete, and the type of duct. Is it polymer or metal? I'll show my Excel and we will talk about the limitations in terms of serviceability limit state. I'll show how it works. As you can see, there is a print screen from design drawings. We have the most severe exposure classes, so I choose them here. And also I need to change the type of polymer, type of duct, because we construct our deck with metal duct. It is cheaper than polymer. And with that metal duct, we will have the criterion of decompression and frequent load case. What does this mean? When cars traffic are on the deck, the normal stresses around the duct, at least 25 millimeters from it, must be compressive and not tensile. As we know, if the tendon is located at its furthest position from the neutral axis of the cross-section, it creates the most significant impact. That is why I will add the checking point of stresses in the cross-section at the distance of 125 millimeters from the bottom and top fibers. You can see them here from the data from section. In other words, this criterion allows us to have some tensile stresses at fibers, but not much. Let's return to the presentation. Here you can see how I'll check the stresses under construction stages and stresses during the operational phase of the deck. I hope that the load combinations that are seen there are well known to you. Quick reminder is here. Of course, there should be more loads, such as temperature loads, differential settlements, etc. Here it is, main loads. Let's consider the result of stresses at construction stages and at stages when the deck is under live load. I will also show the results at frequent load case and characteristic load case in post-Cs. So I go to MIDAS, results, stresses, beam stresses PSC. Before, when we were creating this section, I mentioned about Z1 and Z3 distances that we just talked recently, 125 millimeters from the bottom and from the top. Here are those points, 5 and 9, 8 and 10. We need them to check the decompression criterion. Now I'll show the stress state at each stage of construction. For example, construction stage 2. To check the stresses, we need the summation effect. This summarizes a number of effects. The set is always different for reactions, forces, and deformations. These are primary and secondary effects of pre-stress, and the secondary effect of creep and shrinkage. In the future, we will need this separation of effects. So I'll go to TAP report where I have prepared some images of stress diagrams at each stage. We start from the stage 2. This is a stress diagram of the top fiber. Values in megapascals. You can see they do not exceed the permissible values. Quick reminder, the limitation for compression is 19.2 megapascals and 2.8 megapascals for tension. Then stresses at the bottom fiber. I'll show you the stresses at stage 3, where we stress the first segment and construct one more. Then we are going to stage 4, where both segments are stressed. Here are top and here are bottom stresses. Stage 6, MIDAS shows us stresses at top and at the bottom. This is the last stage where we stress tendons. For example, here we do not exceed the permissible values of tensile stresses at the bottom fiber near the support section. Just if we have some bigger values, then I can check at the level of decompression. And there I will find that, for example, this is the bottom stresses at the decompression level, 125 millimeters up from the bottom. And I can find there are only compressive stresses. That means that we are okay. We comply with the criterion. Stage 7, we remove the scaffolding. Stresses are okay. Stage 8, we have at asphalt. Stage 100 years. This is the top and this is the bottom. Let's see what's going on at the frequent load case. There are top stresses at frequent load cases and there are stresses at the bottom fiber. All are compressed. And characteristic load case. As you remember, at characteristic load case, we shouldn't exceed 24 megapascals in compression for that grade of concrete. This is the top fiber and this is the bottom. Let's go back to the presentation. This is important to remember, as designers usually intuitively try to make more compression by pre-stressing, thinking that this is more reliable. But increasing the stress margin is not only uneconomical, but it also increases the permanent compressive stress in the concrete. Thus, creep strains increases and displacements in the joints and the bearings. In addition, a large number of cables leads to overloading of the cross section during casting and generally worsen the quality of the structure. We've finished with checking serviceability limit state. Now it's turn of ultimate limit state checking. But for that reason, we need to get on with the nature of secondary moments and what it is and how to account for it. In order to understand what secondary moments are and where to take them into account, let's us consider a three-span continuous beam. It is statically indeterminate two times. To reveal the static indeterminacy, we will use the force method. By inserting two hinges into the intermediate support, we will remove the redundant link, thus obtaining three statically determinable beams. To restore the continuity of the girder, we need to apply it to the ends of these girders in the places of removal of extra links hinges. Bending moments, which will rotate the cross section of the ends of the neighboring girders by the same amount and make the cross section rotates together. By making the equation of the force method, we will find these reactions in the redundant links. Draw the bending moment diagram from the reactions in the discarded connections and draw the diagram from the external load in the split beams, single beams. By adding two diagrams, we will get the final one of the final bending moment diagram in a three-span continuous beam from the external load. To highlight, we've got the diagram from the load in simple beams, and we've got the diagram from reactions which restore our original continuity, the diagram of moments of static indeterminacy. Next, I'll show you equations for the method of force. When you have free time, with these equations, you can check those bending moments from the previous slide. This is the primary structure where we need to find the redundant links. Here is the bending moment diagram of indeterminacy. Good luck. Now let's consider how works the same scheme under pre-stressing. Uniform loads on statically determinate spans can be replaced by parabolic pre-stressing cables fixed on neutral axis at the ends of the beams, thus creating bending moments in the statically determinate beams and identical to those in the previous design scheme. The pre-stressing force and the eccentricity with respect to the beam's neutral axis can be selected so that the resulting moments are equal to the moments from the uniformly distributed load in the previous scheme. Consequently, we obtain exactly the same bending moments and the same beam end rotations. As we found out in the last task, the moments of static indeterminacy are 80% of the moments in statically determined beams from uniform distributed load. In this in this pre-stressing scheme, the same moments, the same proportion of the load moments must be applied to obtain the moments of static indeterminacy. In order for the beams to be continuous, it's necessary to apply the same moments as for distributed loads in the last scheme. I mean 80% of P multiplied by EC. These moments must be applied to each internal supports. These continuity moments are called secondary moments or parasitic moments, MP. Then, the pre-stressing moments at any point of the continuous beam is P multiplied by E plus MP. Thus, we have proved that continuity moments, due to pre-stressing, are of exactly the same nature as continuity moment due to external loads. Here is a comparison for simplicity and clarity. Free bending moments and continuous moments are caused by external loads, are connected by the laws of statics, and therefore are considered together as a bending moment without separating the moment of static indeterminacy and the moment from the load in a statically determined structure. But it is convenient to separate them in pre-stressing, in particular for the ultimate limit state resistance verification. See Eurocode 7.6.5. We have considered a special case with parabolic ropes on the neutral axis, which leads to secondary moments equal to 80% of the force if the rope had the same eccentricity and the same tension force, but its shape was different, that parabolic, or it was fixed below or above the neutral axis, the final rotation of the simple beams would be different, and consequently, the parasitic moments required to restore geometric compatibility or continuity would also be different. The cables that lie below the neutral axis of the geoda bend the geoda upwards, requiring the secondary moments to act in the other directions to restore compatibility. Therefore, secondary moments reduce the moments at the support but increase the moment in the span. It should also be noted that secondary moments change the reactions at the support. In non-split statically indeterminate structure after prestressing, even though the sum of the vertical and horizontal components of prestressing is zero, additional support reactions arise. As an example, let us consider a two-span beam prestressed with one tendon. Two-span beam, one support in the middle, and a single-span beam with the same length as two-span, but no vertical connection at the intermediate support. In a two-span geoda with pre-stressing and no vertical connection in the intermediate support, the geoda will have deformations of their form. It can be seen that in statically indeterminate pre-stressing system with connections at the support, additional reactions arise, which hold the structure against buckling at the intermediate supports. Thus, the moment from pre-stressing in the structure can be represented as the sum of the statically determined moment equal to P multiplied by E, where P is the compressive force and E is an eccentricity, and the moment from secondary reactions. We've finally come to ultimate limit state. Let us consider a single span pre-stressed beam. In this beam, the resistance moment is easily determined. We have selected it at serviceability limit state, and their force in tendon is P. And with it, such a moment, P multiplied by LA at the stage of working load, serviceability limit state. In such a beam, the restraining moment at all stages is from P multiplied by LA and is equal to the moment from external loads. I mean, it depends entirely on the presence of reinforcement in the section. In non-split beams, the external moment is counteracted by P multiplied by LA as well, but also by the secondary moment. And the secondary moment, firstly, when checked by ultimate limit state, has its own and the secondary moment, firstly, when checked by ultimate limit state, has its own safety factor. And secondly, it can be present in this section without tension reinforcement. I repeat that the secondary moment can be in the section in the absence of reinforcement in it. And thus, the restraining moment does not fully depend on the presence of reinforcement in the section. And we can't conclude that it will increase as much as the force in the cable. This is when we place the force in the cable by the design resistance of steel. Let's simulate a situation when a working load cars is driving on the bridge. The stresses in the over-support section are within the permissible limits due to the presence of high strength reinforcement P multiplied by E and the secondary moment MP. As I said above, here they are of the same sign. Then something very heavy accidentally drives onto the bridge. In this case, the span should not collapse. The concrete will enter the plastic zone, the stresses in the reinforcement will increase to FPD, but the second component of the restraining moments, MP, will decrease. And it's not possible to simply say whether the bridge will hold under the ultimate load or not. You need to calculate the cross section. So to summarize, at this stage of loading, at this stage of loading of the structure, ultimate limit state, checks must be carried out for continuous girders. Further, I will take the moment acting in the cross section without the force from the P multiplied by E, but only in the part of P multiplied by E. Otherwise, there will be an overestimation of the load-bearing capacity because we will take into account P multiplied by E reinforcement 2 times. Now let's go to MIDAS and have a look what load combinations I created for ultimate limit state. For ultimate limit state, I created only one combination. It includes dead load, and you can see that it is an envelope. It has dead load with coefficient 1.35 and with coefficient 1, with factor 1. Also, this combination for ultimate limit state has pre-stress, and again, it is an envelope. It contains 2 effects with different coefficients. Each effects consist of tendon secondary, creep secondary, and shrinkage secondary with factor 111 and with factor 1.2. And life load. It also might be an envelope of different cases of load groups added below. Here I use only GR1 group, so it's not my case. But if you have more life load combinations, you can add them here and assign the type envelope. So I have only one 4.1 load case for ultimate limit state. Now let's check the structure at ultimate limit state with the tab design. Here I click design. I will choose pre-stress concrete design. Our standard is Eurocode 2. Then click on design code options. There we need to adjust the cement class and strut angle. Sometimes you need to change it You remember, the smaller the angle, the more shear resistance you can get from the transversal reinforcement, but less resistance of concrete strut. Also, we need to adjust what output parameters do we want to have from MIDAS. At serviceability limit state, we've already checked stresses at construction stages, stresses at service loads. We don't need to check principal stresses because the section of the main beam is quite thick. So I'll put tensile stresses and ask MIDAS to calculate, for example, crack control. In terms of ultimate limit state, I will ask MIDAS to calculate bending, shear, and torsional, all three. Click OK. But to be able to do so, to accomplish this task, we need to assign conventional reinforcement to the section. So here I'm showing you the section of the main beam. As you can see, there are bars of conventional reinforcement. I create them with input method 2, with polyline. Just draw line and tell what pitch, what distance between bars I want to use. And of course, the diameter. Also, don't forget to fill data for shear reinforcement and torsional reinforcement as well. And click the same rebar data for I and J end. Close. Then we go to the tab Design Parameters, Serviceability Load Combination tab. As you remember, at Serviceability Load state, we have three types of load combinations: quasi-permanent, frequent, and characteristic. Each of them has different requirements or limitations. So when you create all these load combinations, it will appear here, and you need to assign to each window each combinations as it is done here. Then exposure classes. Yeah. The top of the beam and the bottom of the beam, this surface, they have different exposure class because the top is covered by waterproofing material and the bottom isn't. So for top, I will assign XC4, and for bottom, I will assign XD3. And of course, choose all the beam. Click Apply. Next, we will go to Modify Materials. Here you can see that I've already modified. You need to add just a conventional reinforcement class here. And after that, recalculate the model. It is already done here, so I don't need to the recalculation. Close. Next, we go to Design Positions. Here we ask which elements we need to check. I will ask all the beam to check all the beam. Again, choose all the elements and click Apply. If you want the report about one particular or few particular elements from the model, you can ask MIDAS to create it in Excel file by choosing like that a few elements. If you choose all the beam, it will take too much time, so don't do this. Click Apply. After that, let's ask to perform design. It will take some time. Now it's done. Let's go to pre-stress concrete result diagram. We will ask to show flexure diagram. I click OK. change the units. There you will see that there you can see that design bending moment isn't bigger than resistance bending moment. Resistance is depicted with green strips. Let's check shear. It's also, we have a big margin. That's because I didn't use all the combinations. So we didn't take into account settlements, temperature effects, and so on. And torsion. Everything is okay. What about serviceability limit state? Result tables. We asked, for example, we will have a look at stresses in tendons. Check tensile stress for pre-stressing tendons. Here I will check units again to megapascals. FDL1, stress on tendon at anchorages. FDL2, maximum stress in tendon along the length of the member away from anchorages immediately after anchor set. And you remember that we do not exceed some permissible value, so we need to check this stress with the stress that we accepted for jacking. And here how we do this. So, for example, here is the stressing force for one tendon accepted in the current model. So there is the stress in it, and it is the immediate, it is stress after immediate losses. It's for green tendon. You can see 1311. And what next? We can see that it doesn't exceed permissible value, so we can increase our jacking force and make it around 1480 megapascals if we need it. Next, stresses FLL1, maximum stress in tendon after all losses at the last stage. Yeah, and this is the allowable stress in tendons, but it is in reference to the old version of Eurocode. It's a characteristic tensile stress of pre-stressing steel multiplied by coefficient 0.75. So we checked ultimate limit state and serviceability limit state with a pre-stress concrete design module. Now let's go to the presentation again. We are almost finished. Now we are deformations at reaction section. Here is the table from the MIDAS help, which explains what effect is taken into account for which type of results. In order to obtain the correct displacement in the deflection joints and bearings, it's necessary to calculate not only the displacements due to temperature, but also the deformations due to elastic shortening, creep, and shrinkage. These deformations tend to act in one direction, which can we see in tab results, then go deformations. I'll show. Now let's go to the tab result deformations. For example, for this pen, I'll take into account the deformations for the expansion joints from the stage where I added asphalt. for the bearings from the stage of deactivation of the temporary supports, scaffolding. Now let's go and check reactions. So tap result, click reactions. Here I will add a post-CES mode and choose load case 4.1 for ultimate limit state. I'm asking MIDAS to show me reactions in the local axis because I rotated support nodes towards fixed support at pier 3 to get the result aligned with the scheme of bearing. Now I'll show only support nodes. And go to the plan view. You can see that all coincides with the bearing scheme. Wow, now we have finished with the result analysis and we are going to the last part of the webinar, fourth part, how to adjust cables. Let's go back to the presentation. I'll try to answer how to play with positions of tendons to get the better result without changing it in MIDAS Civil each time. We all know that the primary moment is found simply by multiplying P by E. And for the secondary moment, I'll do the following procedure. First, insert a hinge into the beam above the support, for which we construct the moment influence line. Then apply a load to this hinge node, 1 radian rotation, and adjust angle to get equal bending moments at each side of the hinge. So firstly, we apply 0.5 to one node and radian and 0.5 radian to the next node, which are very close to each other. Secondly, we calculate the difference in bending moment at the section we applied the rotation. And thirdly, find the proportion concerning the angle. So in my example, final rotations are depicted here. They are about 0.5. Then we need to obtain the bending moment diagram from this load along the beam over the length and divide these figures by stiffness, E multiplied by E. So thus we obtain the value of the line of influence at each point along the length of the span for the secondary moment at the point where the hinge is put in at the support. And then you just need to draw a line between the secondary bending moment at pier 2 to the secondary bending moment at the pier 3. And you will get a bending moment diagram of the parasitic pre-stressing effect for your continuous beam. I'll show you my Excel file. What I did, I put there my spans and height of the section. Then I do the procedure that I described before in MIDAS Civil and got the following figures. Here I got the figures from 1 radian rotation I divided by the stiffness and multiply it by primary bending moment. After that, I sum all what I got, and finally, I got the secondary bending moment at pier where I put a hinge. For example, at this picture, it's about that support. And next support, I did the same on the other sheet, and I will get secondary moment influence line over the third point pier. Of course, I have a profile of the tendon to be able to calculate the primary moment, which I calculated here. Here's the graph of tendon alignment. I got two bending moment of secondary effect of pre-stressing. Next, I just can join those values with the straight line, and it will looks like that. Red line. And the blue line is the primary effect. Red line is the secondary effect. If we sum them, we will get the total bending diagram from pre-stress. Now let's go to MIDAS and I'll show how it is organized there. Here is the same main beams with support. I'll show them with supports. Here, I call it the second pier. I insert a hinge and a load here. You also can assign rotation load at the end of the beam where hinge is inserted. And I got those figures. I'll show you beam release. It's not possible to see, okay? So I take these figures, put it in my Excel with the length of the element, and did the procedure that I just described. Now let's change bending points in Excel file and look what will happen with the bending moment. Here I can move bending moments along the length of the beam. For example, I can do this 0.2, and you will see that the final bending moment has changed. And here the figures are different from the previous one. However, the distance from the tendon to the neutral axis remains the same. So we have proved that for the same section height, we can obtain different bending moments due to pre-stressing by moving the bending points along the length of the beam. Go back to the presentation. Here you can see secondary moment influence line over the third pier. And here values that influence on the secondary bending moment at point 1, here the point number 1, when we apply statically determinate bending moment P multiplied by E. The values here is the ratio of the bending moments to the displacements that caused it. Here is the formula that what I did in Excel. So I've finished with my presentation. Thank you very much for your attention and for your time. I hope that I sparked a little interest in the pre-stressing. And now I am ready to answer your questions.